how do you verify and validate something, for example, like a PINN algorithm?
I think that PINNs are a really good way to put physical knowledge into a neural network model. The greatest scientific breakthrough of the past 10 years maybe is neural networks. Just because we know the governing equation doesn't mean we know the solution. My preference is start with theory and then kick into the projects. You can sort of generate data for free if you like, which is one of the advantages of PINNs really. So expressivity is the really important kind of property of neural networks. Closed form solutions truly exist. PINNs really only emerged in 2017, whereas finite element methods have been around for decades. It would be faster to solve that one problem with a finite element method than it would be with the PINNs. Really what works well for you is what you should do.
I'm really, really excited, Conor, to have you on the show. I know you've been a long-term fan of the podcast, so finally you made it on the other side of the show. Today we'll talk about physics-informed neural networks, short PINNs, not about engineering in specific, but really like keep it domain agnostic. But before we get started, maybe give the audience a bit of a background, like who are you in the first place and what are you working on at MathWorks?
For sure. Well, thanks very much, Jousef, for having me on your podcast. As you say, I'm a big fan. So, it really means a lot to me to be here and to talk to you. So just a bit of a background on me. So I work for MathWorks. I'm the senior team lead of the deep learning algorithms team. And so my team at MathWorks look after the deep learning framework in MATLAB. So that's the deep learning toolbox. So we are developers who manage all aspects of neural network training, neural network layers, the autodiff system, which all modern neural networks are built on top of. And we have a particular interest in physics-informed machine learning, physics-informed neural networks, or SciML, and kind of building and training those kinds of models. And I'm very excited to talk about it today.
Very cool. So my next question would have been like, are PINNs dead? But I think because you're working on it, the question is kind of stupid. So from your perspective, Conor, do you think like PINNs still have a lot of, like you apply them in a lot of different places, in a lot of different domains? Like maybe talk us a little bit through like where they can be applied. Because
Sure.
I feel a lot of people, especially when I talk to them on events and I don't know, expos and whatever, they think that PINNs are dead, but I'm not sure what you think about this.
Right. Yeah, I mean, that's an interesting question. So I guess what I want to say first of all is that PINNs are a relatively recent idea, right? In kind of the history of physics, if you like. PINNs came about in around about 2017, where they were first proposed. So they haven't really been around that long. Now, in AI terms, 2017 is kind of a long, long time ago, right? But in kind of physics terms, it's relatively recently. And I don't think PINNs are dead. I think that PINNs are a really, really nice idea, and a really good way to kind of put physical knowledge into a neural network model. We know neural networks are important or useful because they're extremely expressive nonlinear functions that you can use to train to do any kind of complex problem that you can't solve easily analytically. And we know from many centuries really of mathematical physics that differential equations are the most effective way to describe the physical world that we live in. Right? They've had incredible success, if you like. And I don't need to tell you, Jousef, about the power of differential equations like Navier-Stokes or whatever your favorite nonlinear PDE might be. So PINNs are just a way to put those two things together, right? So when we know the governing equations of some process or some system that we're trying to study, it makes sense to use those equations in our study of that system. And equally, it can be very useful to use neural networks to study those systems because we know that neural networks are highly expressive, trainable algorithms, right? It's really the greatest, if you like, the greatest scientific breakthrough of the past 10 years, maybe, is neural networks and the power that they have and the kind of the amazing applications that we've seen emerge from the deep learning community. So we want neural networks in the solution of these complex problems as well. And PINNs is just a very natural way to put those two things together, right? So just to dwell on the definition of what a physics-informed neural network is, well, it's a neural network that has been trained with a partial differential equation or a system of partial differential equations, including the governing equations and the boundary conditions and so on, with those equations applied in the loss function as you train that neural network.
Yeah,
That
that's. Mhm.
that's all it is. That's all it is, right? So, um, in a nutshell, I think it makes sense to if we have the knowledge whereby we know what the governing equations of our system are, and we want to use neural networks in our solution somehow, that we don't throw away the knowledge that we already have, that we take that knowledge and we add it into the training process. Um, to me, it just seems like a very natural thing to do.
Yeah, it kind of seems logical, right? You have a specific loss function to kind of constrain the system to make sure it follows kind of the physics that we kind of prescribe to the system. I'm wondering, where's the difference between a classical neural network and, let's say, I'm going to train my neural network on test data from the real world? Isn't the physics implicitly in that data? So why would I need a physics-informed neural network in the first place?
Sure. Yeah, that's a really good question. I mean, you're absolutely right, provided the data is clean. So if I've observed my data without any noise, then the physics would be kind of implicitly in the distribution of the data, the test data that we've observed, and the training data.
Hmm.
And so you're absolutely right that that you can hope that the physics of the problem has been imbued into the network simply by virtue of the training data that you've observed. Um, so pins is just a way, though. A PDE in the loss function is just a way of making doubly sure, um, from a certain point of view, that you really know that the physics is in there. I mean, you know the physics anyway, so you might as well incorporate it into the loss function. On a more technical note, I think there have been papers that have shown that when you train a neural network using the pins losses, you actually get a better fit. You get a better fit in terms of when you extrapolate in your test set outside now of the training set, your network has done that little bit better in terms of learning.
Hmm.
And the precise reason for that, might be an open question, or why that might happen. Um, so yeah, I guess deep learning is an empirical science, and empirically we've seen that having pins and pins losses can help the model generalize. Um,
Hmm.
but of course, there's opportunities that come from using pins losses as well. If you wanted to make sure that your test set and your training set accurately determine or accurately display all of the physics that you know is there, then you have to go and collect that data, which can be expensive. And one of the advantages of pins is that you do not need to gather so much labeled data, right? Pins is inherently an unsupervised learning technique in the deep learning parlance, which is nice because it means that the data is kind of cheaper to collect. You don't need to run expensive simulations. You just choose the data points that you're interested in tuning your neural network to. So you choose the inputs, but you don't need to generate targets, as it were.
Hmm.
So it can be cheaper.
Yeah. What would you say is the most difficult process in the whole, like from beginning to end, building of a pin network? Is it? We'll talk about data, right? Is it defining of the loss function then, Connor? What would you say?
I think it really depends on the problem that you're trying to solve, right? So if you have a very simple system with a simple governing equation, um, then the most difficult thing might be just like writing the code or converting the equation into the loss function. Um, for more complicated problems, you have more headaches in other parts of the pipeline, right? So you might have to choose an appropriate network architecture, for example. With neural networks, there is no one size fits all in terms of the structure of the neural network that you ought to use or that you're best, um, will give you best performance. So that can be an issue as well. There's the data pipeline, whether you need to use mini batching and so on to save memory, what hardware you're trying to target to get the best performance, as well as the precise construction of the loss function itself, right? So yes, it could be writing down or converting into code the partial differential equation that you know. Um, But of course, and then specification of the boundary conditions, as well as the maybe the momentum equation. Um, and often those are combined uh, um, in the loss function, just via summation. So you specify let's take Navier-Stokes, right? Yeah, I think you and I both have a particular affinity for the Navier-Stokes equations, as should anyone who has ever heard of the Navier-Stokes equations or has come into contact with them. They're a really beautiful set of equations. But suppose we want to train a physics-informed neural network to solve the Navier-Stokes. Well, what we'd have in our loss function would be the momentum equation, which is the really juicy part. But then we also need to specify the boundary conditions in order such that the problem is closed and there is a solution. Um, but what we typically do with pins is we just linearly combine those two losses. So we have some residual from the momentum equation, and then we have some other residual from the boundary conditions or the initial condition. And you kind of it's one of these deep learning dark arts, of which there are very many. But you have to choose what weight you want to give to each component of those loss functions. Um, in order that they're well balanced. So you don't want any one term to dominate the loss, because then the neural network will struggle to properly minimize across all elements of the loss.
Mhm.
Um, and that can be a very tricky thing in practice when you start to actually try to build a PIN solution. It's also a very active area of research, and I wouldn't profess to be fully up to date with that research, because I think it's a struggle for anyone who follows deep learning research to stay fully up to date. It's kind of like trying to drink out of a fire hose. There's just so much research that's being published day on day, and it's all fascinating. But anyway, there is some research on how to kind of successfully balance the losses in pins. You can have learnable weightings and so on. Is one approach that I've seen that looks to be promising.
Yes.
So in
Yeah.
answer to your question, I realize I've gone off on a very windy road there, but in answer to your question, I think that the difficulties in a pin solution really depend on the problem that are at hand, and it could be the geometry of the network, for example. It could be the specification of the pin's losses themselves, including the boundary conditions. It could be whether you want to include some experimental data in the loss function as well, because of course one of the real advantages of pins, I mean, I say one of, there are many advantages of working with neural networks, but everything is kind of composable. So I can just take my pins loss and I can add on the kind of experimental loss as well from any sort of observed data that I might have. And I can just combine them and compose them. And this is one of the really nice things about the deep learning world, is it's very flexible in that regard. Um, so the biggest issue that you might have, might be different if you were to solve another pins problem. Um,
I see. What are some of the disadvantages then of pins? The reason I'm asking, Connor, is because let's say we don't talk about the Navier-Stokes equation, but we talk about a very complicated problem, such as maybe, I don't know, a crash test. There's kind of
mhm.
no analytical solution to define a crash test. So are there applications in the real world where we say, okay, pins might not be that suitable, we just run normal simulations, versus when do I run pins? Maybe they're too slow. Maybe if I know the analytical solution or the loss function, then it's more easier to train. Like, what is the, more probably to pose it differently, like, when should someone use a pin versus a classical simulation?
Yeah, that's a great question. And again, there's been lots of research on this, which is exciting. So I think there's maybe a rule of thumb that's emerging, that is that if a finite element solver and solution exists, that you're probably better off with that. Now,
Mm-hmm.
let me give some of the caveats to that. Um, Uh, so if you suppose that you're trying to solve a problem for which that there is some finite element solver available, um, and you want to solve simply for you're interested in the solution simply at a current set of parameters or some one finite set of parameters. So you're not terribly interested in extrapolating your solution beyond um, the set of parameters that you solve for the finite element method, um, without having to solve more finite element method problems, then the finite element solution itself will typically converge faster than PINNs, and importantly, it'll have more kind of mathematical guarantees of solution accuracy and the existence and so on. Because the finite element method has been around for a number of years, and mathematicians have had time to, go away and work out those bounds and work out the kind of the optimal approach for that problem. So PINNs will not kind of compare well there, and there have been papers that have kind of shown that in terms of time to solution and the kind of final error that you get if an analytic solution were known and you wanted to compare. Or what some papers do is just run a very long finite element solution with a very fine mesh and take that to be the ground truth, which is fair enough. So PINNs doesn't work as well there, probably because PINNs is so young. So like I said, PINNs really only emerged in 2017. So what does that mean? 7 years of time for people to get this right, whereas finite element methods have been around for decades. And mathematicians, engineers, physicists have had a long time to kind of optimize and make sure they fully understand those methods. That's not to say, maybe a natural question then is, all the problems I'm interested in have finite element solvers available, so I guess PINNs is not for me. I don't think that's quite right. So PINNs and neural networks in general, deep learning in general, as a technique, can be better when you're trying to explore parameter spaces cheaply. So if you want to do some design optimization, for example, over a range of geometries, say, it could be very expensive to run finite element simulations for each of the geometries that you're interested in, prohibitively expensive. So what you might want to do is use a neural network technique to find quick, hopefully relatively accurate solutions across that parameter space. So it allows you to do that kind of design optimization that just would not be able to do with finite element method. And so that's one of the advantages of PINNs again. So it's kind of give and take. It really depends on the kind of problem that you're trying to solve. There can be other problems with PINNs that are maybe a little bit more mathematical in nature. So as you know, with nonlinear dynamical systems, often there exists a multitude of solutions. If you have chaotic dynamics, you can understand chaotic dynamics as a random walk between unstable equilibria or unstable periodic orbits or whatever it might be. And so when you try to train a neural network to find the solution of differential equation, you don't really know what solution you're converging to. And indeed, there might exist multiple solutions. And so stochastic gradient descent, which is how deep learning, deep networks are trained, doesn't really have much in the way of guarantees that you're going to get to a specific solution. Whereas finite element methods, because they're a bit more mature, I think can provide certain guarantees for that kind of problem, so they can give you a little bit more stability, or you can be a little bit more certain about the solution that you determine. I guess those are a couple of disadvantages.
Yeah. What I was wondering about is when you work on PINNs at mathworks, like how do you see it happening let's say an engineer is using them in the real world. Do you think it's more like they're stacking PINNs and classical simulations at the moment? So maybe if you want to explore parameter spaces where you assume the solution is accurate, you would use a PINN for quick exploration and then would run a normal simulation. Is that how it works nowadays?
So we do see applications. We do see customers who are interested in exploring parameter spaces using PINNs. But it's important to remember that the goal of those applications is to explore the parameter spaces. So I think it's fair to say that engineers are open to using PINNs as a technique, but they're not wedded to that technique. In particular, they're looking for the best approach. And PINNs may play a part in that for some problems, absolutely. I think in general, the customers that we work with at MathWorks are interested in what I would call embedded AI. Um, so they're interested in using the incredibly powerful techniques that are emerging from all of the AI research and work that's going on at the moment, and and using that in such a way that they kind of get it into um, the devices that are being engineered by these companies, and the products that are being engineered by these companies. Um, and so that can be, it's kind of easy when you think about AI. It's easy to think about the latest and greatest that comes from somewhere like OpenAI. All kinds of amazing video generation and image generation and text generation and so on. Um, but embedded AI isn't always about that. It's partially about that, but it's also about being able to, you know, build something like a virtual sensor. So a virtual sensor might be, a sensor that can pick up some quantity for which, regular or kind of real physical sensors just do not exist, right? So, I mean, for example, it might not really be possible to measure the, I don't know, the outflow temperature inside a jet engine just because it would melt away any real temperature sensor that you try to inject in there. But you can measure
Hmm.
other things, right? You can measure maybe the rate of rotation of the jet engine. And if you have enough things, concrete, variables that you can measure, you can train an algorithm that will take those concrete measurements, physical measurements, and sort of generate for you, compute what the temperature might be. And knowing the temperature might be useful in terms of how you control and monitor the health of that system. And so these kinds of applications, and I realize I'm speaking very loosely here, but these are the kinds of applications that we see, that we work with, that we work with other engineering firms at MathWorks to help them build and help them make the most of AI.
Hmm. I haven't checked it out actually. Is there like a PINN toolbox or something like that? Like, or is it just a general deep learning toolbox instead of MATLAB, for example, that you could use?
So it's a general deep learning toolbox, and within that toolbox, you can use um, you have all the tooling that you need in order to solve PINNs problems.
I
And
see.
part of the work that me and my team do are about writing examples that showcase those tools, building on top of those tools so that there's more functionality available, and that it's slightly easier to do, to build the kinds of to write the code that you need in order to solve a pins problem. We want to make the APIs nice and clean. We're software developers and we're interested in code, and we think a lot about code, and we spend a lot of our time thinking about how code can optimally be written. And so
Yeah.
that's kind of part of the work that we do.
Yeah. Going back maybe to the topic of data, like how do you handle incomplete or noisy data in a PIN?
Yeah, that's a great question. I think that the way that you would do it inside like a pins problem would be the way that you would do it for any deep learning, any machine learning problem. And again, there's a variety of ways that you would deal with incomplete data or noisy data. Um, pins actually lend themselves very well to this because, as I said before, pins are an unsupervised technique, so you do not need to rely on observed data at all. You can sort of generate data for free if you like, which is a
Mhm.
very one of the advantages of pins really. Um, but in general, it's dealing with noisy data is something that you would try to deal with as you train your neural model. Um, uh, so, for example, we have some published examples on our website that show how you can train a neural ODE model for incomplete and noisily sampled data. It's what's called a latent ODE model, and it uses kind of an inversion on uh, the whole pins idea actually. So a pins problem or a pins model is one that any neural network architecture is trained with a PDE and the loss function, or a differential equation and the loss function, whereas a neural ODE is a type of neural network architecture which is defined effectively by an ordinary differential equation, right? So you have, if you like, f dot of x equals a neural network. So it specifies some dynamics that are learned, and you can use well, and so the the forward pass of that network is an integral, right? So it's you work out the time evolution, and you can use that to handle irregularly sampled data, which is really useful, particularly for real life engineering problems. Um, and you can use it to soften away any noisy data that you might have observed as well. Um, there's a bunch of other techniques. I'm not I'm not even going to be able to give a complete list because there's just so many. Um, I think there's an approach of soft losses as well, where you can kind of attach a probability to every observation that you have, so you bake into the training some degree of uncertainty or stochasticity
Mhm.
in the data that has been observed, um, and so on. And I think all those techniques that exist for kind of classical machine learning problems can be applied, can be brought over for PINNs problems as well.
Yeah, I see. That makes sense. I think a logical follow-up question would be the computational resources or the time needed to train these networks compared to
Mm-hmm.
the classical simulation, as you've talked about a couple of
Mm-hmm.
minutes ago, Connor.
Mm-hmm.
Um, do how fast are pins, depending on the problem, of course, but like
Mm-hmm.
how much faster are they compared to simulations?
So compared to the like finite element simulation, you mean?
For example, yes.
Yeah. Well, I think it's generally been seen that training pins is slower and training finite element methods is faster. So to be very precise, that means so for a given parameterization of a geometry and a PDE, say with a fixed Reynolds number or some other hyperparameter, um, it would be faster to solve that one problem with a finite element method than it would be with the pins. Um, but of course, that relies on the classical solution actually existing. And of course, with finite element methods, um, I don't know if they can be extended to more than 3 dimensions, or I don't know how common that is. It's not something I know very much about. I'd be very interested to learn actually. Um, whereas what I do know is that neural networks extend very naturally to higher dimensions. And so, then the classical solution maybe doesn't even exist. You might rely better on pins. Also, an interesting point of comparison is, are pins slower or faster than if I were to just train a kind of classic deep learning problem with,
Hmm.
training predictors and targets. And actually, pins can be slower because pins require the loss function to compute derivatives, right? Um, which effectively means that you have to do more autodiff. You have to do more, backward passes, if you like, in
Hmm.
order to compute the derivatives. And of course, this scales very badly the higher the number of derivatives that you have, right? So, if it's a first order problem, maybe it's not so bad. If it's second order, maybe that's okay. Third and fourth order, it could get worse because the the computational system has to do more work effectively every time it needs to compute the loss. Um, so then when you compare pins with that kind of classical machine learning style of training a problem, pins can be worse. But again, there are these kinds of ingenious tricks to get around this problem. And one of my favorite tricks is something that exploits the higher dimensionality of neural networks, right? So we can very easily scale them up to very high number of dimensions. That's part of what makes them such good learners, is the conventional wisdom. Um, combines that trick with something that we all learn in our undergraduate degrees, which is the conversion of a high order ordinary differential equation into a first order system, a first order kind of
Hmm.
matrix system, if you like. So you can kind of see how that might play well when you're training a pins, because you can take a higher order system, maybe fourth order, and you can turn that into a first order system. Um, just by setting, my second derivative equals the first derivative of some other variable, right? Introducing these kind of these extra variables and then constraining them in the correct way. So you turn everything into a first order system, and then you train your neural network on that high dimensional first order system, so that during training time, you only need to do a single backward pass. You just do it for a higher number of dimensions, but that's
I
fine
see.
because neural networks scale very well for those high number of dimensions. I really like this trick. I saw it at Neurops a couple of years ago, and I just thought that is just a beautiful little trick. And so, there are ways of getting around these kinds of inefficiencies that we see with pins, and the community continues to um, excite us all and dazzle us all with these kind of nice ideas. And I'm interested to
Yeah.
see where that'll go in the future.
Yeah, likewise. What are some of the promises for pins in the future? Like, what do you, for example, expect kind of like pins in terms of like performance problems that they will be solving? Like, will be coming maybe next 5 to 10 years? What do you think?
Yeah, that's a great question. So I think the things that I know about now are really the design optimization problems that we've talked about already a little bit. Um, but I'm interested to see what the community does. Like I said, kind of at the start, it makes sense to me that when the physics is known, that we use the physics when we train neural networks. And so I think we're still sort of scratching the surface and starting to see where the really interesting applications are gonna come from. Um, I wanted to say though that I'm, sort of building on, just pins for a moment. There's this whole burgeoning area of physics-informed machine learning, which
Hmm.
includes pins, but it's kind of broader than pins, right? There's other techniques, and I'm really excited about this whole area, right? I'm really excited about what we're going to do as a community in this area. Um,
Yeah.
we're already seeing things like equation discovery, techniques for equation discovery, which
Hmm.
help us learn new underlying laws of physics. It's a whole different approach, and there's a whole bunch of techniques that are kind of emerging as the toolkit for this physics informed machine learning area, and I'm excited to see what we do there. Um, not to kind of get lost in my thoughts here, which is always a danger when you're talking to me, Jousef. I
Hmm.
apologize about this, but
So good.
so I think that you know I'm someone that comes from a background of being interested and excited in nonlinear dynamics, right? And I think you and many of your listeners will be of the same mind. And back whenever I was learning about nonlinear dynamics, it was just always the case that you needed to know the governing equations, right? Either you were a genius like Newton or Stokes or Hamilton or any of these guys, and you knew how to derive what the dynamics were from physics, um, or you were kind of a very clever mathematician and you could come up with kind of interesting equations that you knew would have some interesting behavior. And I think we're entering into a world now where that's just no longer the case, right? The world that we're entering into now is much more about um, being able to observe dynamics. We observe the data. We live in a very data-rich world now, so we just go and look at it, and we take that data, and then we'll be able to derive from that data what the dynamics are by just feeding that data into some kind of deep learning machine learning system, which will extract the dynamics from us. And then once we've learned that dynamics, then we're able to study all this kind of interesting dynamical behavior
Yeah.
via the neural networks. And I just think that this is a really interesting way for us to learn about the world. And who knows what conclusions we'll draw from it? Who knows what we'll be able to do
Absolutely.
with it?
Yeah, super exciting. I was wondering, this is also one of the misconceptions I think there is about PIN. Also, some of the questions we got in was if we prescribe the loss function, which has a physical meaning,
Hmm.
are we already know the explicit solution, right? So why are we giving the network the solution and then train the network on that solution? Isn't
Right.
that kind of going in circles? Like,
So I wouldn't interpret it that way, actually, right? So
mm,
just because we know the governing equation doesn't mean we know the solution. And again, the Navier-Stokes equations are a really good example of that because
mhm,
they were written down at some point in the 19th century by Navier and then I guess by Stokes, but we didn't know how to solve them. We didn't know a general recipe for the solution, and actually whether or not closed form solutions truly exist was one of the Hilbert problems at the start of the 20th century, and then it remained unsolved throughout the 20th century and became a millennium problem at the start of the 21st century, right? So this is a classic, or the great kind of unsolved problems in mathematical physics. Uh, so just because we know the differential equation does not mean we know the solution. And so when we train a neural network and constrain it to a differential equation, it doesn't mean that we know the solution. And in fact, multiple solutions might exist. And as I mentioned before, the part of the problem is that when you train a PINNs, you do not know what solution you're converging to. Um, or you don't know anything about the multiplicity of solutions that might exist. Um, so yeah, so I don't think that's quite the case. And if anything, um, I think of PINNs losses as kind of a soft constraint, right? So it's a constraint that's applied during training. And you basically train the neural network such that it minimizes the residual between or the residual of the differential equation that you're interested in. And so during training time on the training set, you have some guarantee or you have some knowledge that your neural network kind of obeys the equation, or at least it minimizes it in some sense. But then when you stop training and you go and you apply your neural network to the test set, you don't have that guarantee anymore. In fact, there's nothing stopping the neural network from just breaking the differential equation altogether, especially if you are applying it to regions outside of the training domain. So it's a soft constraint, right? It does not guarantee that the neural network that you train will satisfy that equation, in perpetuity. You just don't have that guarantee.
I see.
So it's really like more, and I think that's why they're called physics informed neural networks, right? They're not called physics constrained neural networks, or they're not called physics obeying neural networks. They're physics informed. I think the choice of language is very deliberate, because they're kind of given a sense of the equations during training time, but after that, it's anyone's game.
Yeah, I see. What part does explainability play in the role? Like when we talk about PINNs.
Mm. That's another really good question. I think explainability is a really important part of AI, and it's equally an important part of physics informed AI. And I think the first thing to say is that we get some level of explainability when we're dealing with PINNs, just for the very fact that we know the governing equations of our system, and then we're able to say, look, we know that this neural network has been trained to satisfy that those equations, right? At least during the training time, like I just said. So in terms of explainability, you know, it's very different maybe from the kind of explainability that we would think about in the general deep learning community, the general AI community. But as a physicist or as an engineer, knowing the equations that govern our system gives us some kind of explainability, right? It's like we know the physics in some sense of what governs our processes. Um, but explainability um, uh, is important more broadly. It can be it can be important in that how you go and speak about the neural network and how you explain what it does. It's just giving you that insight and kind of helping you talk to that. I think it has the very tight relation in kind of engineering AI with what we call mathworks V&V, or verification validation, right?
Okay.
Um, So, earlier I talked a bit about embedded AI, and that's really about, like I said, trying to get AI algorithms into engineered devices. And, we can't just deploy any old algorithm into, say, a car or an airplane. There are a very strict set of rules and regulations that any algorithm that's going to be deployed to a safety critical device, such as a car, has to obey, right? Um, it's a very, very different situation to say some like a retail website which might do some kind of like user segmentation using AI, try and look at the click-through rate and try and predict what it's going to be. There's no safety issues, safety critical issues with those kinds of applications. So those algorithms are not subject to the same level of scrutiny that algorithms in real engineered applications are. Maybe they should be. Maybe that's another conversation. But all that is to say is that when we're looking at embedded AI, we're really very interested in verification and validation of neural network solutions. Um, and I think that leads us on to this whole world of constrained learning. Um, and one constraint might be like a Pinn's loss, right? Like a set of
Mhm.
partial differential equations. But there are other, often more basic constraints like convexity, monotonicity, and so on, that we might want our solution to obey. And critically, we might want our solution to obey those before and after training, right? We want to make sure that after training's done and we've got our algorithm and we're just kind of using our algorithm, that it's still going to be, say, monotonic, right? And I'm really interested in this, and we're really interested in this at MathWorks because, because exactly of this application. But where it leads us to is that there are a whole set of network architectures that we can build that give us these kinds of constraints in what we call an implicit sense, right? So you might think of it as an implicit bias, right, towards monotonicity or something like that. And we've kind of already seen in the early days of ConvNets how those kinds of implicit biases are really important for machine learning applications, right? So ConvNets are the kind of power horse architecture that's driven a lot of the advances in AI. Many of the early kind of stunning wins that we saw from neural networks were driven in the image domain, were driven by ConvNets, things like first there was AlexNet, then there was VGG, and then there was ResNets, and there was GooglyNet maybe in between, and all these kinds of really cool architectures. And they were all ConvNets. They were all ConvNets applied to image classification. And one of the reasons that those ConvNets did so well in that image classification domain was because convolution is an implicit bias, or it's an implicit bias within the network architecture that
Mhm.
somehow captures translation invariance, which is an important part of those classification tasks, right? So if I have a picture of a cat and I move the picture of the cat to another part of the image, if I just shift it a little bit, it's still a picture of a cat, right? And so any algorithm that's able to make that connection from some set of pixels to the label of, it's a cat, um, has to kind of respect that translation invariance, and that's what convolution does. It's an implicit bias, and it just helps the whole model train. Um, if you were to compare that, for example, with an LSTM, uh, long short-term memory recurrent neural network, a very popular recurrent neural network, a very popular architecture that was used back in the early days for things like language modeling before it was superseded by transformers. LSTM does not have translation invariance, and so if you try to flatten out all the pixels of that image and treat them as a sequence and feed it into an LSTM, you do not have that translation invariance, and therefore it's just harder for the LSTM to learn that problem, right? Um, no, that was kind of a long segue, but what I'm trying to say is that there are similar implicit biases that we can imbue into neural networks to make them satisfy things like monotonicity, things like convexity. And this is a really exciting strand of research for us. It's a really exciting application for us and for our customers. And we see it as enabling embedded AI.
This is really cool. Yeah, I didn't know that. Thanks for informing us there. I was wondering, you talked about the verification and validation aspect. I think I've shared it already in my newsletter. There is some really good blog posts on the MathWorks blog about verification and validation, especially for AI.
Mhm,
Could you maybe walk us through, like, how do you verify and validate something, for example, like a PIN algorithm?
mhm. Yeah, that's a good question. So there is a lot of great content on there. You're right. We haven't looked at V&V for PIN's algorithms in detail yet, or at least I don't think we've
Okay.
published anything on it. So what I can
Hmm.
tell you now are my thoughts, but they may well be incomplete. I guess
That's
that's a
fine.
caveat I can
That's fine.
apply
No
to
worries.
everything that I say.
Yeah.
But so I think that the real sense of validation that you'd want to kind of pursue is that you have some system of equations, and you want to make sure that your neural network actually obeys those equations even during testing, right? So after training.
Hmm.
So the kind of V&V that I think that's verification and validation that I think I'd want to go for that kind of problem would be to compute those losses on the test set and try to evaluate how well the neural network continues to obey the laws, right? Um, and you could see actually how it would lend itself really well to something like incremental learning. So incremental learning is a kind of paradigm, neural network paradigm, whereby you never really view the network as being trained and done and then just deployed into the wild. You have a much more fluid sense of the network's training process, and so what you do is you come up first of all with a metric, and for pins that metric would be the pin's residual, right? Like how well
Hmm.
does the network actually obey the PDE? Um, and so you could compute that metric after the network's been trained, and if you see that it's starting to grow, right, that all of a sudden the neural network is not doing a good job anymore of actually obeying the PDE, then you can say, all right, well, let's stop here and let's retrain a little bit, and make sure that that metric, that pin's residual, is back down again into the good region. And then we'll carry on, and we'll just keep monitoring things as we kind of deploy the system. We'll keep checking in on that metric, and then we'll kind of fine tune as necessary. And this is just another example, though, of the nice things that you can do with neural networks, right? They can be trained in that kind of online fashion, as we'd call it. You just let the data come in, you do some gradient updates, you update the model, you check that it's still giving you good metrics for the the metrics that you care about, and then you redeploy.
Hmm. That makes sense. Okay, interesting. And one of the questions I had, because we talked a lot about theory and some of the practical tips that you've mentioned earlier in the podcast. Let's say I want to get started using the deep learning toolbox and specifically like get my hands dirty with pins.
Mm-hmm.
Like, walk us through like how do I start, like from beginning to the end? Walk us through how I train my own algorithm with my data that I have.
Mm-hmm. Yeah, that's a great thing to think about, right? So I think that the way I would recommend starting this is it's kind of sketched out in an example that we have online that I encourage every listener here to go take a look at, and maybe we can include a link for that.
Hmm.
Um, and it very much mirrors like my own journey and how I tried to learn about these things. And so first of all, you start with some differential equation. And if you're just learning about pins and you just want to learn about them, then you pick something with a nice closed form analytic solution. You could look over your undergraduate notes if you were lucky enough to do an undergraduate in one of these kinds of things, and pick one of your favorite ones from there. Um, and so you define that equation, and you work out the analytic solution as well, and write that down because you want something nice to compare against. Um, and so then you've got your kind of baseline equation there, and then what you want to do is start to think about the neural network, right? What's the neural network? What kind of layers am I going to include in my neural network for this problem? And that can be really tricky, right? And there's a couple of things that you have to think about. Like you have to think about what's the input shape of the data, right? So am I talking about sort of one-dimensional data coming into the neural network, or two-dimensional or higher?
Hmm.
And you have to think about what kind of layers are in the neural network. How is the information going to be processed? I think typically in pins we see what I would call multi-layer perceptrons, um, which is a set of fully connected layers and nonlinearities. Um, and in general, actually, it can be very hard to build a neural network architecture. So if you're starting from scratch, or if you're just learning about pins, it's having an example to hand is a really nice thing to have because you can kind of follow the recipe there. So you specify your neural architecture, um, and then you start to you generate data, right? So you choose what data points you want to train the network on. So you need to sample some points in the domain. And so you do that. Normally that can be straightforward. Sometimes there's sort of pitfalls in there as well. And then you want to actually train the network. And in MATLAB, when you train a PINNs network, you use our custom loop framework, what I would call our custom loop framework. So you want to specify a number of what are called epochs, like the number of passes through the training data that you want to do. You write a for loop, and then you compute the loss function, right? And you compute derivatives of the network or gradients of the learnable parameters in the network with respect to that loss function. And that's the bit where you get to do PINNs. That's the bit where you actually write down the differential equation that you want to solve, and you sort of bake that into what we call the loss function, right? Or cost function is another name for it, I suppose. And what I like about doing this in MATLAB is that MATLAB as a language is something that we have tried I guess for many years to make MATLAB as close to the mathematics as possible, right? As opposed to other languages which I also love, like Python, or maybe more lower level languages like C++, which are much more programming languages, right? They're
Mm-hmm.
really good languages for general purpose programming, but they're a little bit further away from mathematics, right? And so when you write down the PINNs loss in MATLAB, we try to make it look and feel like writing down mathematics. And actually, that particular task is really something that concerns my team. We're interested in making that PINNs loss be as close as possible to the mathematics, something we think about a lot. So you write that down, and you write your loss function, and as I say, you compute derivatives with respect to that, which we have a nice call in MATLAB for. It's called DL gradient, nice and easy.
Mm-hmm.
And then once you've got your gradients, then the basic step then is to update your network based on those gradients. And for that, we use standard neural network update rules like stochastic gradient descent with momentum, or ADAM, which is like called adaptive momentum or something like that, or use something like LBFGS, which is an update rule that's very good for small amounts of data.
Mm-hmm.
And you just keep updating your network in this loop over and over, and you monitor the loss, and you wait until your loss is small enough. That is, you wait until your residual between the PDE and what the network outputs is kind of small enough, and then you stop, and then you're done. And then you've trained the PINNs.
That's that sounds very simple, at least in theory. I think what we should do, Connor, is maybe after this podcast, plan for a deep dive session where you maybe demonstrate how this is actually being done,
Sure.
and then maybe people can check it out and yeah, give it a try themselves. Cool. What we're going to do now is to wrap up the podcast in a bit. Is I'm going to go through some of the questions that we got from some of the listeners of the
Awesome.
podcast. First question by Dimitro is: in what specific ways are PINNs utilized when addressing non-homogeneous environments? Considering that existing examples primarily demonstrate problem-solving scenarios with simple boundary conditions and homogeneity. It's a bit long, but hopefully you get what he means.
It's a great question. It really is. So what I would interpret homogeneity to mean is that you're solving a PDE in a kind of single uniform domain. And what you want to do is then with kind of non-homogeneous boundaries is to solve something like a fluid solid interaction system, or maybe a PDE across something with like an air water boundary. Um, by the way, I think these are really fascinating problems. Some of the postdoctoral research that I carried out was on exactly these kinds of problems, where you have an elastic or a porous medium, and you want to learn something about the aeroacoustics as you have kind of very fast fluid flow past this porous medium.
Mm-hmm.
But in that research, it was a very, very limited kind of domain that we were trying to solve, and produce results for analytically. So I can see how it'd be very, very exciting to build a solution that captures this in a more generic way, right, to arbitrary domains. Anyway, that's a long way to say. Look, I don't know. I think that's a very interesting research question. I wonder if there are papers that have tried to approach this. Um, I'd be very interested to see what comes up. Uh, and if no such papers have been written, then I think we should write one, because this is a great research question. To kind of make a stab at an answer, I'd suggest something like this. Why not parameterize each domain? If there's a kind of finite boundary between different domains, if I'm interpreting the problem, to the to the correctly, why not have different neural networks across each of the subdomains, and try to solve them separately, right? Compute an update for each neural network kind of independently, and apply boundary conditions, uniformly or uniquely to each domain. I guess that's kind of the classic approach, right? Like when um, in mathematical physics, when you first encounter a nonlinear problem, what do? You linearize it, right? And you learn about the behavior of the system in that linear domain. And I guess I'm just suggesting a very similar thing here. So
Mm-hmm.
you've got non-homogeneous domain. What do? Well, turn it into a sort of set of homogeneous domains, and try to solve it that way.
Great. Next question by AJ. I don't really see physics-informed neural networks applicable for irregular geometries. Physics-informed GCNNs come to our rescue here. I'd be interested to hear your and Connor's thoughts on this. Probably Connor's thoughts, because you're the expert.
Well, I think this is absolutely correct. Yeah. So when you're dealing with an irregular geometry, those are just well parameterized by graph neural networks, right? But here I see pins is something that pins, as I understand it, does not specify a neural network architecture, right? Pins is just how you define your loss function.
Mm-hmm.
And so if you can express the partial differential equation um, in such a way that it applies to the geometry that you have, which is parameterized by a graph neural net, then you can combine the two approaches, right? Get
Mm-hmm.
the best of both worlds. And I think there has been some research that's been done in this kind of thing.
Interesting. Okay. And as we said, Connor, every relevant resource we'll link in the description, and then people can also reach out to you individually if they
For
want
sure.
to.
Yep.
One question from Ali. Could there be potential benefits in providing ML algorithms with access to a comprehensive library of established physical problems to optimize the selection of appropriate physics for the cost function?
Well, this is an absolutely awesome question. I think there certainly would be benefit in that kind of system. And for me, it's very reminiscent of an idea that I've seen in other domains in deep learning, an idea that people call foundation models. So, for example, in the image world, you have a bunch of what are called foundation models, neural networks with a good set of kind of um, biases towards the domain that they are kind of trained on and used for, right? So networks that are, say, good at representing images, and then if you have any task that concerns images, then typically these neural networks can be adapted in such a way that they're useful for that task.
Mm-hmm.
And
Yeah.
we see the same with text, right? So things like ChatGPT and so on are kind of like a foundation model for natural language. And then any task that you want to do that involves natural language, you might start with a foundation model and fine tune it to that specific task. And we see the same for audio, right? So for all these kind of natural physical domains, we see foundation models. And I see no reason why there could not exist a foundation model for dynamics, right? So something that kind of just has some natural intuition about dynamics. It could be physical dynamics, or it could be anything. As we know, not all dynamics problems are physical. I think of something like the Black-Scholes equation, right, which is
Mm-hmm.
used somewhere over in the world of finance. Um,
Yeah.
but some kind of foundation model that knows about physics in particular, I think that would be very useful, because I've seen it be useful in these other domains.
It's very cool. Yeah, fascinating idea for sure. Two last questions. One by Siddhant. If one would like to start learning about pins, should project-based learning be the way to go, or should we understand the theory first and its functionality properly first?
This is a great question. I think there's like pedagogical element to this that I don't want to be too prescriptive about. So I'm just going to give my opinion here. But I think as with all kind of learning approaches, really what works well for you is what you should do, I think. But for me, so to speak personally, I think that it's really, really powerful to have have an understanding of the theory first, and really try and absorb that and soak it up. Um, and But then not to stop, right? Then to take on the more excuse me, take on projects, and work your way through some practical examples. In order to put that theory into test, because that's kind of I think the two go very hand in hand, right? I think you can kind of get a good overview from the theory and build some deep intuitions, but then you really cement those by building on them via projects and via practical examples. I think that if you and this again, this personally speaking, if you jump straight into the kind of project based approaches, you miss a few things, right? So it's maybe not clear to you why you're doing certain things, or in what order you can do certain things, or what steps you might miss. And so I think that if you really want that depth of understanding, you don't often get it alone from a project-based approach, right? You need some of that theory in there. Um, but yeah, so my preference is start with the theory and then kick into the projects.
Yeah, that makes a lot of sense. Fully agree here. And then last question from the audience. If your model inhabits integral symmetry or invariance to specific parameters, how can this physics be incorporated in NN apart from incorporating the PDE that governs our data in boundary conditions and initial conditions?
Yeah, this is a great question again. I think it touches on some of the topics we were talking about earlier in terms of constrained learning and so on. Again, I think there's lots of research in this particular problem, in the neural network community, um, around what we call equivariance, or symmetric neural networks, and it's really a way of adding that inductive bias or implicit bias, if you like, into the neural network architecture. And so there's a whole load of theory about how we do this, and what kind of bounds we can input into the network. I think that strand of kind of thinking is the way to do it. As I talked about earlier, the application of um, PDEs in the loss function and in the boundary conditions and so on is really a soft constraint, right? It doesn't really constrain the model at all. And it would be the same with symmetries. So if you applied a symmetry in the loss function somehow, then it would only be a training time constraint. It wouldn't necessarily hold afterwards. Um, but I think this research is really very interesting because it can be a toss up between strictly obeying the symmetries and so on, and maintaining expressivity. So expressivity is the really important kind of property of neural networks. They're extremely expressive nonlinear functions. Some architectures are in fact universal function approximators, so they can approximate any function, which is very handy. So you want to be able to constrain your neural network to those symmetries in such a way that you do not break that expressivity, and you still give the model enough room to grow and to learn.
Excellent. I think that was a very extensive answer. Hope the guy who asked the question is happy with this. Any closing remarks from your side, Connor? I think we are over an hour right now, so maybe
Oh
some
wow,
last
yeah.
motivating words to the community regarding pins, or maybe just getting started with pins.
Sure, yeah. Well, I think that pins are a very, very exciting avenue of physics, of mathematical physics, and of engineering physics. I think it's a useful tool that every engineer should want to learn about and to know about. I think the engineers of the future will learn about this technique in their undergraduate courses, which is a really you know, interesting kind of thing to dwell on. And I wish everyone well in their journey with physics-informed neural networks. I hope they enjoy them as much as I have enjoyed them. And I just want to say, Jousef, it's been a real pleasure to talk to you today. I've really enjoyed every minute of it. I can't believe we've been talking for over an hour, but as they say, time flies when you're having fun, or time flies when you're talking about physics-informed neural networks. Anyway,
Exactly, yeah. Let's see, maybe there will be a second part in the future. And as promised, we'll put every relevant link to pins and also mathworks resources down in the description.
Sure.
to make sure everyone can get started their journey on pins. But
All
yeah,
right.
thank you so much, Connor.
Cool. Are we wrapping up? Are we going to put a pins on it?
Yeah, definitely.